Hello everyone, welcome to joining my talk today. This talk is prepared for the conference Advances in Computational Mechanics ACM 2023, a conference celebrating the 80th birthday of Professor Thomas J.R. Hughes, who is my academic grandfather. I'm Chanok Park from Mechanical Engineering of Northwestern University, and I'm a student of Professor Convolution. The title of my talk today is Convolution, Hierarchical Deep Learning Neural Network, C-HiDeNN, and Isogeometric C-HiDeNN, in short C-IGA theory development. Right, next slide is about the motivation of my talk or research today. So have you ever heard about Software 2.0 or differentiable programming, right? You may have heard about this. So this term, Software 2.0, was coined by Andres Karpathy, who is ex-senior director of AI in Tesla and founding and current member of OpenAI. Yeah, he mentioned this in his famous blog post, and we would like to focus on the engineering application of the Software 2.0. So we want to start from the engineering Software 1.0, which will be Abacus and other standard finite element solvers. What they do is developers specify the problem, whether it is a linear problem, nonlinear problem, time-dependent problems, and design the algorithms for that specific task, and they divide a complex task into subtasks. So the programmer needs to program the subtasks one by one and combine them and solve it as specific problems. But if we move on to the Software 2.0, what we have is a lot of database. And we have an optimization problem. So we will define a problem into an optimization problem. Those programs are differentiable and also optimizable. One example from Software 2.0 will be ChatGPT. This is one system of our software, but it can solve multiple different tasks, right? So we want to view the engineering point of Software 2.0 in our research. And we believe this convolution hierarchical deep learning neural network C-HiDeNN theory is a good driver toward the engineering software 2.0. So we have this list of publications recently, mostly on the convolution hidden theory. And I'm going to cover C-HiDeNN and convolution IGA and how we can leverage the idea to train a general data. All right. Let's just start from the very basic example. Here is our data set. The black dots are data points. We have 90 data points. And we want to do the regression from P to U. And we're doing in two different methods. One is the piecewise linear regression with two segments on the right-hand side. And the fit-for neural network with three hidden layers on the left-hand side. And they are doing almost the same thing in terms of the regression, right? So their loss functions are almost the same. But the difference here is the number of parameters, the training parameters. For fit-for neural network, we have 251 weights and biases. Whereas for the piecewise linear regression, we have only 3 parameters to fit. Those are U1, U2, and U3. Since you have so less number of parameters, the training time or optimization time will be very short. And of course, the memory usage will be very low. But how does this possible? This was possible because we leveraged our mathematical knowledge to fit this data. When you just look into this data, it has a sudden slope change, right? And this is a 1D regression problem. So we can leverage piecewise linear regression with 2 segments. So those mathematical knowledge came into picture. Now we are having a very small problem instead of solving a large FFNN problem. So our idea is, can we leverage this idea for solving partial differential equations? That was our research question. So we applied the same theory or same idea to solving a partial differential equation. Here, the black dotted box is a 1D element interpolation. This is a piecewise interpolation, and you can view this as a standard linear FE, finite element. That's this. So for this element-wise interpolation, it goes into the right-hand side box, the black dotted box here. This is for one element, and we have the same structure with different coefficients for different elements. So element 1 through element n. We call it this hierarchical DNNs, deep neural networks, and they output the solution layer. And one thing here is, if you go into this element-wise neural network structure, this has only 2 hidden layers, and they're not fully connected. They're only partially connected, right? And their weights and biases are represented in the function of nodal coordinates and nodal field variables, x and u. So these are not just random weights and biases. Instead, we are using the knowledge of nodal coordinates and nodal variables. So after this, we construct a loss function. Instead of just standard mean square error, our loss function is constructed from weak form. So now this is a potential energy of the physical system. So after having all this neural network structure, what we're going to train is the nodal coordinates and nodal variables. They are not just random weights and bias of a fit-form neural network or physics-informed neural network. And when we solve only for nodal field variables, this is mathematically equivalent to solving finite element analysis. But if we fix nodal solution and update the nodal coordinates, it's kind of training data. So in this structure, in this neural network structure, we can actually solve and train at the same time using an optimization problem with auto-differentiation. This is a key idea of our first paper published in 2021 on the hierarchical deep learning neural network. We call it HiDeNN because it has a hierarchical structure. So here's one example of HiDeNN. We are solving a Poisson problem where these black dotted lines are the exact solutions, and the blue ones are the equally spaced mesh and the finite element solution. And what we do with this red plot here is that we want to optimize the nodal coordinates at the same time. So those nodal coordinates are now moving toward this peaks and valleys. So we are actually training and solving at the same time with using the HiDeNN structure. Then what about convolution HiDeNN? Why do we need convolution term in front of HiDeNN? So here's a example comparison between HiDeNN interpolation and convolution HiDeNN interpolation. The key idea is either linear interpolation or nonlinear interpolation. If you look into the left-hand side HiDeNN, the interpolation is piecewise linear, and this is quite similar to linear finite element methods. And the neural network structure looks like this. So element-wise neural network has 2 hidden layers, right? 1 and 2. But in convolution HiDeNN, C-HiDeNN, we have additional hidden layer that represents the nonlinear interpolation. Since we have this additional third hidden layer, we'll be able to achieve this nonlinear interpolation. So if you compare the performance, the number of parameters are the same, 6 and 6, right? We are actually trying to find out this nodal use for these 6 points. But our interpolation scheme is different. With C-HiDeNN, with this third hidden layer, we are able to achieve this higher order continuity or nonlinear interpolation. So the same idea goes on to solving the same problem, the partial differential equations. So we are using the same structure for each element. But in this case, with this third hidden layer, this convolution layer, we want to leverage the information from the surrounding node to construct the nonlinear shape functions like this. And this is very different from the standard higher order finite element methods, because in higher order finite element, they increase the elementary degrees of freedom. and construct a higher order Lagrange polynomial, Lagrange shape functions for that element that leads to the increase of the global degrees of freedom. But in our case, we still use the same number of degrees of freedom as linear finite element, but we leverage the nodal connectivity of the surrounding nodes to build a nonlinear interpolation. So that is a key difference, because in our case, we are not increasing the degrees of freedom, so we are still having the same, I would say, the level of difficulties in solving a problem, solving an equation, but still can do the higher order interpolation or approximation. So in this structure, we can do the same thing. If we want to solve only for nodal variables, it's going to be solving. But if we want to also update the nodal coordinates and other parameters A, S, P, they are shape parameters of our C-HiDeNN interpolation. They are trained. So this is the key idea of engineering software 2.0. So let me briefly go over the mathematics behind the C-HiDeNN interpolation. So C-HiDeNN interpolation can be written in this way. One is, and this is a standard finite element shape function. And this W is we call convolution patch functions. And they are combined together to form the convolution interpolants and tilde. So for each function, the FEM shape function and convolution patch function should satisfy this total 4 conditions, and everything together, we are able to achieve canonical data properties and reproducing order, reproducing conditions. Those are all defined and proved in these theoretical papers listed here. So if you are interested in it, please refer to these papers. I once mentioned this about the degrees of freedom. So this exactly shows that for a higher order finite element, you have more degrees of freedom, right? Compared to linear FEM, you firstly had only 729 nodes, or nodes in your mesh. But if you go to p equals 4, now you have over 35k nodes. But in our C-HiDeNN interpolation, we are still achieving the same reproducing order, p equals 4, but instead of increasing the degrees of freedom on each element, we are leveraging the nodal connectivity of the surrounding nodes. So we call this red dotted box as a patch domain. So we are leveraging the nodal connectivity to build the nonlinear interpolation. So what's the outcome of this? We are still having the same size of the global stiffness matrix, but the bandwidth, now we are having a wider bandwidth of the stiffness matrix. So that is the difference. Okay, due to these features, that means without increasing the DOF, we can achieve higher order interpolation. Our program, Convolution HiDeNN, is efficient. That means it is fast and accurate. So this example solves a 2D Poisson problem with linear FEM and higher order FEM and C-HiDeNN. And to achieve the same level of accuracy, 10 to the minus 3, linear FEM requires 10 to the 4 times more DOF than convolution HiDeNN. Even cubic FEM p equals 3 needs 10 times more DOF than C-HiDeNN with the same polynomial order. In terms of the total solution time, C-HiDeNN is 140 times faster than linear FEM, and higher order C-HiDeNN is even more than 3,000 times faster than linear FEM. Note that everything was coded on GPU program. So FEM and C-HiDeNN are all coded with GPU, but still our method is quite faster than finite element. So up to now we have shown that convolution HiDeNN is good. But why do we need this one, convolution IGA or C-IGA? The answer is we need to convert from CAD to mesh. That is, most engineering designs are produced from CAD models. But if you want to do the analysis of that model, you have to convert that CAD model into a mesh. So that is very cumbersome and labor intensive. That's why Professor Yuri Bazilevs and Tom Hughes write a paper on IGA, isogeometric analysis, in 2005. So we want to do the same thing with the scope of convolution hidden. We call it C-IGA. And first, this paper is on the single patch, only one patch, theoretical development on C-IGA. All right, so the key idea of the C-IGA is that extension of C-HiDeNN with an exact geometry borrowed from the IGA. So if you look into this problem, a plate with a quarter plate with a circular hole, if you construct an finite element mesh, they are linear meshes, right? Their boundaries are just straight lines. But if you construct the same mesh with IGA or C-IGA, you are having the smooth boundaries for that element. That means you are able to reproduce the exact geometry. That is the key idea of IGA and C-IGA. All right. So how we can do that under the C-HiDeNN framework? So this was the C-HiDeNN interpolation, isoparametric. So we have n shape function, the FEM shape function, and W as the convolution patch functions. Together with these two, we are having C-HiDeNN shape function, right? So if you look into the convolution patch function, these convolution patch functions are built with a two set of functions. One is the radial basis, this green one, and the polynomial basis as the violet one or purple one. So these two functions satisfy the canonical delta and reproducing properties. So these A and C coefficients are found such that it satisfies these two conditions. So this was the idea of C-HiDeNN. But in convolution IGA, what we want to do is to reproduce the exact geometry coming from IGA. And IGA geometry was built by the IGA basis functions, which are B-splines or NURBS. So this is a classical IGA mapping. So what if we can replace this polynomial basis into IGA basis functions? Can we reproduce, in such case, the exact geometry? That was the idea. So inside this convolution patch function, we want to replace this polynomial basis into the IGA basis. It can be B-spline basis or NURBS basis, but anyway, we are replacing the polynomial basis into IGA basis. That is a key. And we proved that if we do this, we are able to achieve the same mapping as isogeometric analysis. So even with this convolution hidden setting, which is quite similar to standard finite element, we are able to achieve the exact geometry of IGA. So this illustrates the mappings of convolution IGA. But if you look into these mappings, so finite element is a linear boundary of element, but IGA and C-IGA, they are matched exactly. And if we compare C-IGA or C-HiDeNN into IGA, the key differences are the DOFs. So in IGA, the degrees of freedom are attached to the control points. We call it control variables, right? But in FEM, C-HiDeNN, and C-IGA, they are all attached to the nodes. So it is shown here. So if you have this physical domain or physical mesh, you have the control points, and those control points are mostly not on the surface of your physical domain, right? But in C-IGA, they're exactly attached on the physical domain, just like FEM. But still, our element has the exact boundary coming from the IGA mapping. Due to this feature, that IGA degrees freedoms are attached to the control points, and they're not on the physical surface, they require additional constraints for the Dirichlet boundary conditions, the displacement boundary conditions, for example, or even the force boundary conditions. But since convolution IGA degrees of freedoms are exactly on the physical surface, No additional constraints are required to impose the displacement boundary conditions. So it's just like a FEM mesh refinement. We can do that with C-IGA. So this slide clearly shows the difference between these two. So if you have this IGA mapping in the parametric domain and physical domain, if you want to do the mesh refinement in IGA, at this mesh, for example, if you have the null spaces, we have to refine the mesh globally, like this, even though we actually didn't want to refine this mesh around here. The corresponding physical mesh will look like this. So we are actually adding the nodes in the parametric domain, and it results in the global refinement. But if you look into C-IGA, we can actually do the refinement using finite element software, just like standard FEM, because our degrees of freedoms are attached to the nodes. So we can do the local refinement like FEM, and the corresponding refined mesh in the physical domain looks like this. So just like this convolution hidden, our convolution IGA can have higher order accuracy without increasing degrees of freedom. That's why our model is much more efficient than the standard ones. So for the given level of accuracy, 10 to the minus 4, convolution IGA requires less degrees of freedom than IGA or FEM. C-IGA is orders of magnitude faster than linear FEM, and it takes similar computation time as quadratic FEM. Next, due to the features that C-IGA degrees of freedoms are attached to the nodes, we can even solve an unstructured mesh like this square and triangular hybrid mesh, or triangular elements like this, without sacrificing the accuracy of the approximation. So this is a key feature of convolution IGA. My next topic is on the convolution hidden tensor decomposition. Here, the tensor decomposition is a projection-based reduced order model. That means for a multi-dimensional problem, we want to decompose the n-dimensional problem into multiple one-dimensional problems. In such way, we can reduce the degrees of freedom a lot because the DOF growth changes from exponential growth into a linear growth. So now we want to recall this hidden and C-HiDeNN interpolation, this slide that I covered like a few minutes ago, how we actually train this data using our C-HiDeNN or hidden framework. It can be viewed like this. Suppose that we have one data point, pk star and uk star, and we find out that this data point belongs to this segment, p of 1, 4 and p of 1, 5. Those are nodal coordinates. Then we find out the shape function of that linear element. The corresponding shape function values are n4, n4, and n5. And the corresponding nodal variables are u4 and u5. And loop over every data point and do the same thing and measure the mean square error. So this is our prediction and this is the ground truth from our data. So this is a mean square error. And finally, solve an optimization problem. I'm going to optimize with respect to those u1 through u6, the 6 variables. In C-HiDeNN, we are doing exactly the same thing, but since we leverage the surrounding nodes to build the nonlinear interpolation, our interpolation at each data point has a wider shape functions. So now we have n tilde from 2 to 6. We have 5 shape function values and corresponding 5 nodal variables. And we do the same thing, construct the loss function and solve it. This is a benchmark problem widely used in machine learning community called Borehole equation. It has 8 inputs and 1 output. And these are the description for that variables. And you can see as the number of training data increase, the training time of FFNN becomes much larger than C-HiDeNN. And this is a comparison in between widely used machine learning algorithms and neural networks and HiDeNN and C-HiDeNN. We randomly generated 1 million training data without noise. And we also note that the extreme gradient boosting, the XGBoost, is one of the best ML algorithms as of today. So XGBoost won multiple Kaggle competitions and is very widely used. Let's compare the result here. So HiDeNN and C-HiDeNN requires the lowest number of training parameters, as you can see here. It only requires less than 2,000 parameters. On the other hand, random forest XGBoost neural network and pruned neural network requires a lot more degrees of freedom. That means our method is memory efficient. Also, the training time of C-HiDeNN is over 100 times faster than your network. And also, our method is the best in terms of the accuracy. So it has orders of magnitude less mean square error compared to other methods. And this is the only case where we achieve 0.9999 R-squared value. And finally, the inference time of C-HiDeNN and HiDeNN are the lowest. That means if we have a new data point, measuring that data point using our trained model is much faster than the other methods. The reason is we have the smallest number of training parameters. So our neural network structure is very simple. But still, we are achieving very good accuracy. And one important thing to mention here is that the XGBoost and random forest, they are tree-based methods. That means they cannot be easily differentiated. But our methods, including the neural networks, are differentiable. That means we can solve inverse problems quite easily using the gradient-based optimizers. So we envision the C-HiDeNN trainer can revolutionize the inverse problems in engineering applications. All right, here's a summary of my talk. The first part of my talk was on the convolution hidden. So convolution hidden satisfies the canonical delta and the partition of unity, and higher convergence without increasing the degrees of freedom. For the convolution IGA, it's an extension of C-HiDeNN, but can achieve exact geometry borrowed from the IGA. And also, we can do the versatile mesh adaptivity without adding degrees of freedom. Finally, I introduced the concept of convolution hidden tensor decomposition. And the trainer, our C-HiDeNN trainer, requires less memory, less trainable parameter, faster training, and prediction time, and suitable for inverse problems. All right, thank you for listening today. And if you have any questions, please leave comments below. And thank you all for watching this video.